All right.
Hello.
Hi, how are you?
Good. How are you?
Oh, I'm good. Glad it's almost the end of the week, but right.
Yeah, for sure.
I'm gonna get started. I know this is this video is at a weird time for a lot of people. So thanks for showing up. All right. Let me get this. How's this class going for you? Is it going okay? Is everything not too bad? I'm hoping.
Yeah, I'm getting the concepts and hang of it.
Oh, good. I think this isn't too bad of a course as compared to some of the other electrical ones. I think they can get challenging. So this one isn't too bad. So I'm glad. Hopefully it stays that way. We're almost halfway there. So all right. Can you see my screen the week 4?
Yes, I can.
All right. Perfect. So I'll post this too after, obviously. So any questions? Oh, how do I?
And I worked ahead in your class because I'm in residential wiring too. So that one's a little more time consuming.
Yeah, I know a couple people are in that. Are you like on the route to be an electrician? Is that the route you're going?
No, I'm getting the certificate, but so with my current job, my boss asked me if I would ever want to be one of the analysts out in the field.
Oh,
And he told me that I would just need to take like these selected courses, and for like 10 more credits I could just get the whole certificate. So I just went ahead and just did that.
oh, wow. Well, that's exciting.
It's gonna be, yeah. And my mom's boyfriend is a master electrician, and he said he's gonna have me do some wiring over at my mom's house that she needs done.
Oh, to like help show you
So
how.
yeah, because I like hands-on stuff. Like I need to do things to be able to, learn, I guess.
Hard being online, being a hands-on learner. So
Yeah, but those modules, I like them. I like those modules.
yeah, I
It's not like exactly hands-on, but
about as close as you can get.
yeah.
All right.
I had to,
So this week, it talks a lot about normally open and normally closed circuits. So basically the difference between them. And then it also talks about them in real world applications. So that's kind of what we'll talk about for the majority of this. I don't think it'll take very long. Especially too with, I kind of base it off however many people, like if anyone's struggling, I might do a longer video, but looking at the grades from this, the people who have taken this one, I don't know if you've taken it yet, but like look at the grades from this one. They're pretty good. So I kind of have focused on a few of the harder portions of it. And then, so yeah. And then I'll talk a little bit about batteries and how to basically calculate voltages in batteries. So this is the first little bit here. Just a quick recap on what a parallel circuit is. So basically just how the parallel circuits, we have our electrons flowing through, and that parallel have multiple routes to take. And ultimately, like in order for a battery, or not a battery, in order for like a load, like a light bulb to light in a circuit, your electrons have to go all the way around like that path. So they have to go from one end of the battery, which is right here where these lines are, to the other end. So that's important for like in a minute here when we talk about normally open and normally closed circuits. So definitely knowing the difference there is really, really important. The other thing here on the right bottom. So this little door is an example of a switch. So that's typically how it's denoted in electrical applications. A switch is going to be denoted by this little door. Right now, this picture here is an open circuit. So an open circuit, basically, what that means is its electrons are not flowing. So you're not basically lighting your load. You're not doing anything. And that's because when the electrons are running around here, they have to stop right here because it has to be a closed path for electrons to get from one end of the battery to the other. So that with this door being open, nothing's going to work. So basically any electrical application in the basic sense, if you have an open circuit, it's not going to work. So for example, a light switch, when we flicker a light switch off, you're opening the circuit basically. And obviously it's a little more complex than that, like in terms of like a battery or in terms of like a light bulb in your house, but it's basically the same concept that when we turn it off, we're opening the switch, which that's something that's really challenging for a lot of like students. I've found, like the fact that when we're talking about it being open, it's off, but when we're talking about it being closed, it's on. So definitely that's something to remember in a minute here, but just knowing that this here is an open circuit, which means that we're not having any electricity flowing, is the most important thing. So again, just a bigger picture here showing that this is an open circuit or an open switch. So your switch is like a light switch, which turns something on or off or opens and closes your circuit. So that's all this is saying here. A few of the other important things here, we have resistance, which we already talked about a lot, your DC source, so your battery, obviously with your positive and negative end, and then your load, which your load might be something like a light bulb, which is typically what we use here as in like basic electricity courses. When we talk about circuits and electricity, we talk about loads as light bulbs because it's the easiest thing to think about, because we know that when that light turns on that we have a perfect closed circuit. Okay, so this is when we get into the NO and NC stuff. So NO is normally open and C is normally closed. I think this diagram on the right is the best picture of that. So basically for a circuit in real world applications, they're either going to be normally open or normally closed. So a normally open one is a contact that does not flow current in its normal state. So energizing it and switching it on will close the contact, which allows your current to flow. So basically normally open is this picture in the left corner, where we can see how if we go back to this situation, this is a normally open circuit. Let's say, like if this is how the circuit is as it's at its normal state, it's a normally open circuit because we have an open switch here, which means that we can't have electricity flow. The only way, if this was a normally open circuit right here, the only way to get electricity to flow is we need to close this switch. So in real world applications, what that means is you might have a stop button and you have to, or you might have a go button and you have to push that button and that triggers this to switch, close. Just like another application, again, going back to the light switch, let's say we have a normally open switch. That means that we have a light that's normally off, right? It's normally open, so our switch is open, so electricity is not flowing with it. If we press a light bulb or press a switch up and the light turns on, we're closing the circuit. So a normally open circuit is one that in its normal state does not have electricity flowing through it. And the reason for that is because this door is open. On the contrary, a normally closed is when is a contact that flows current in its normal state. So flows current, which is current again, is just electricity flowing through a wire. An example of this would be, let's say that you're working on a machine in a plant, right? I work in manufacturing plants, so it's a lot of my examples. So let's say we have a machine that's constantly on. It's constantly blowing air into the machine or however it's on. And this would be something that's normally closed, because that means that in its normal state, no one has to touch anything. The machine's just on. But let's say there's a red button. When you press that red button, the machine instantly turns off. This is an example of a normally closed situation, because that means that in its normal state, we don't have to do anything. Its electricity is already flowing. But as soon as we press that button, our circuit's going to open and then it's going to turn off. So that's the difference, right? I guess that's the main difference. Hopefully that makes sense. So normally open just means at its normal state. So before anyone touches it, our machine is not running because the switch is open, so electricity can't flow. And a normally closed, it means before anyone touches anything, the machine, the light, everything's already on, electricity is already flowing. We have to do something in order for it to turn off, in order for us to open that switch. Okay, so basically I already said this, but basically in a series circuit, if there is no switch, NO again is normally open switch, your power is not flowing in the circuit. Again, we have to push a button to get power to turn on. And note that it says a series circuit, because this is where this kind of gets challenging when we talk about the difference between series and parallel. And I'll show examples of why It's not always the case for parallel, but in a series circuit, if you ever see an NO switch, you can automatically know that if, unless we press something, power's not flowing. So when you have an NO circuit, it's closed and you have like a button is pressed, that's when power is going to start. So again, normally open, we have that switch open, we press a button, it closes that switch, and now electricity can flow. In a normally closed situation, pressing a button is going to stop the flow, which is exactly what I said here. So this is the example I have here. Let's say we have a light that's constantly remaining on. We know that this means that it's a series circuit. So we know this means it's in its normally closed situation because the circuit is constantly, having electricity run through it and run through it. If you push a button and that light turns off, it means that the circuit is now open, and so electricity stops flowing. But basically that's the main thing. And then obviously I don't want to just have to keep repeating it because I know it's probably boring. So hopefully that makes sense. If it doesn't, just stop me. So this is where this can kind of get a little bit challenging. So in some situations, and especially in real world applications, you don't just have one switch running the whole control of an electrical panel. And this is exactly an example of where we have to break it down piece by piece. So problem is a simple robot, which, might be like the robot that at any type of plant or any type of factory that's, packing something or, doing whatever automation, robots. So let's say a simple robot has the following control circuit. So it has an on-off power switch controlling the power to the robot and the controller, a dead man switch wired to a normally closed relay, and an e-stop push button switch tied to a normally open relay on the teach pendant, which is used to manually move the robot. So basically the question is, in what situation will this robot work? So here we're dealing with three things. We're dealing with an on-off switch. We're dealing with a dead man switch wired to an NC relay, which relays are just another fancy word for switch. I think that one of the videos doesn't work this week, but basically a switch or a relay it's just a switch. I don't really think in this class we could go into any detail on exactly what it means, but just know that it's the same. It's really the same thing. So we have a dead man switch, the on-off, and the e-stop button. So let's say we need this robot to work. So the first thing, obviously, on the on-off switch, we know that the power must be on, right? That one's pretty self-explanatory. But for the second one, our dead man switch, since it's normally closed, right? It says right here, dead man switch is normally closed. It means that our circuit is constantly flowing when we don't press anything. So that means that you do not want to press your dead man switch. So first you have your on-off switch on. You do not press your dead man switch because pressing it is going to open that circuit. And then we have an e-stop. So the e-stop, it says right here, is normally open. A normally open relay. So that means that we have to press that one because normally open means that we're not having anything flowing. So we have to press something or trigger something to make it flow. So in those situations, we press this on-off switch, we press the e-stop, but we do not press the dead man switch. So basically, that's kind of a question you might have. Obviously, it might have it a little bit differently. Like it might be a normally open relay, not a normally closed, but just know that, if you break it down step by step, you can see what you need for something to turn on, which I think is really unique kind of or interesting for like real world applications to kind of see it here. Like anytime you press a button to kind of know them, this form of electricity, this is why you're pressing the button. It's to turn it on or to turn it off, depending on if you have an NO or NC. Okay, so now this is where it gets a little bit challenging. So I mentioned series and parallel and how that comes into play, and this is how. So in a parallel circuit, we know that it has multiple pathways for your electrons to go. So that means if one pathway has an open circuit, your electrons could still flow because they're going to flow through another pathway that had a closed circuit. So for example, looking at this example right here, if we had a switch on one of these branches, so like right here, our electrons couldn't go down this path, but they could still go like this, and they could still go like this. Hopefully you can see my mouse, but basically as long as there's one path for them to go, it's okay. In series, if there's a switch and it's open, there's nowhere else for them to go, but in a parallel there is. So that's where it gets a little bit challenging. So if you have a circuit with two switches in parallel that is normally closed, so that means flow through a circuit is started without us doing anything, and you open one switch, there's no change in your flow. And that's because though the electrons aren't going to be able to go through one of those pathways, there's still a full pathway for them to go. So as long as you have one normally closed situation in your parallel circuit, then it's going to have no change in your flow or your current. They're still going to be flowing through and lighting up the loads. But it will stop in that one path that has the open switch. Okay, so now let's see an example where you have 4 push buttons in parallel with only one light bulb at the end. Okay, so 4 push buttons, like let's say the push buttons would be like on a panel, like if you're working like on like a machine, and you have 4 buttons, and you have to have electricity to run the machine. Or in this situation, it's a light bulb. So you have to press, you have 4 buttons, and that ultimately factors in how the light turns on. So how can you get the light bulb to light in this example? So again, 4 push buttons in parallel, and you only have 1 light bulb at the end. So in this situation, you only need 1 button press. And that's because, and this again gets pretty challenging, but it's because you only need 1 button press because it's a parallel circuit, and all we need is one complete circuit, one completely normally closed circuit for them to flow. So you don't have, I mean, you could press them all. If you press every single button, it would flow, but you could press 1, you could press 2, you could press 3, or you could press 4. It doesn't really matter. It's still going to light because it just needs one flow. So kind of the example I have on the bottom there. So if you're running an industrial machine and you have to press 3 buttons at once for the machine to work, you should automatically know that's a series circuit. Because if we have to press 3 buttons at once, that means that pressing just 1 button isn't sufficient enough, and you have to press all of the buttons. So that means that we have a series circuit, because if it was parallel, we should only have to press 1 button, because that means it will have 1 circuit for them, completely closed circuit for them to go through. So that kind of is 2 examples of questions you might get. So the first one, this one that's in bigger, is showing you how you can tell if it's if you're given that it's parallel, you only need basically 1 light bulb or 1 button to press to get it to work. And we also might have questions like this where we have to make the determination if it's a series or parallel. And again, you can make it by knowing how many buttons you're pressing in order for the machine to work. Okay, so that's basically it for the normally open, normally closed. So the main idea is, again, know the difference between normally open, normally closed, and know the difference between how they work in parallel and series. Hopefully that made sense. For anyone who watches this later, again, if you have questions, just email me. I'd be happy to find time to meet or do whatever. So the last little bit here is really quite simple, but basically we're just talking about the battery. So we haven't really touched on what the battery is yet. Now we're finally getting into that. So your battery is essentially a part of your circuit here. Typically, we've always talked about batteries, but we've never really talked about them. But we've always had them in circuits. They're just right here where it says the DC source right here. They're typically always denoted by like these straight lines. Anyways, so your battery is a portable power source. Main keywords are power source that's consisting of 1 or more electrochemical cells with external, basically within your electrical device. And they do this because they carry, or they are important to electricity and circuits because they carry electric charges for a long period of time, which is important to actually get your electrons flowing. So again, we talked about how the load or your battery is that push or the pull that's getting your electrons moving. So after your electrons are basically how your electrons work is they're separated in the battery and they're stored on the anode. I know that probably does not make any sense, but basically in this situation right here, we have our battery, and there's 3 main components of our battery. We have cathode, which is the top here, which is denoted more on the positive side. So cathode typically always means positive. So if you ever hear like a cation, it's positive. Anytime it's the CAT, it just technically means the positive end. Anode's the negative end. We know batteries have a negative end, and then your electrolyte is somewhere in the middle there. So basically when we talked about at the beginning here, this electrochemical cells, this is kind of what's coming into play here. It's really, we don't really have to talk about the structure of the battery, but just know that it carries electrical potential, and that is ultimately what's pushing or pulling those electrons to move. So our electrons are all getting separated in the battery, and they're getting stored right at the bottom here in the anode, and then they can start to move. So the reason that it's important that I mentioned this, and really the only thing you need to know about batteries, is that after electrons are separated, they go to the anode. And the reason for that is because that's how they're flowing here. They're flowing from negative to positive. You can see that the anode, all the electrons are here, because that's where they're stored. And we know that electrons have to flow through a wire. So electrons are going all the way around and up here into the cathode. So they go out of the anode and into the cathode. Main thing though, again, just memorize basically that they're stored in the anode. Other thing to note here, so all batteries in a voltage are the same in parallel. So if we have two batteries wired in a series, the total voltage is the difference. So I'll show an example of what that means. So basically, it's easier for parallel if we ever have to calculate batteries. So if you have multiple batteries, all batteries in a voltage are the same, have the same. So let's say that we have an example like this. And again, this is the really only thing, the reason that I have this slide is because there's only two key things you need to remember. And it's that this first thing here, they're stored on the anode, and then know the difference between how to calculate the total voltage given batteries. So it's easy for parallel, and it's also easy for series. It just requires this math. So let's say we have an example of we have a 9-volt battery and a 3-volt battery wired with the positive ends of both batteries touching, negative, positive, positive, negative. What will be the total voltage in this circuit? And that will be 9. So you can see right here, 6, 3, 9 volts. And that's because we just add them together. Okay, so this is basically the most important slide for batteries, and it's just calculating them in a series like I just did. Okay, I think I showed this wrong. Yeah, I did this one wrong. Forget that. Forget this little portion right here where it says a 9-volt battery and a 3-volt battery, and it shows this. I explained that wrong. It should be like this. Okay, this is easy. I just totally messed it up. I'm so sorry. So let's say we have an example like this. So we have a 10-volt battery and a 3-volt battery wired with the positive sides of both batteries touching. So it looks like this. And we know that because we've seen that before. Like when you're putting in batteries, like, you know, like in like a light, you have to like stack the batteries. And let's say you put them in like this, where our positive ends are touching each other, you can still calculate voltage. And the way to calculate voltage there is that you just take the difference between one battery and the other. So in this situation, 10 minus 3. You wouldn't do 3 minus 10. You always would do the bigger number minus the smaller number. But on the contrary, if you have a battery that's stacked in this way, so you have negative, positive, negative, positive, so you have opposite ends touching, you're going to add that voltage. So then your total voltage is 13 volts. So basically what this is telling us is that when we have situations where we have negative, positive, positive, negative, it's really not an ideal situation. And you never want to do it unless you wanted really low voltage, because when we do this situation, we're losing voltage because we don't get to add them together. We have to subtract. So in situations where you're trying to increase your voltage, you'd want situations where you have the batteries at the opposite ends touching, because that means you're maximizing your voltage by doing 10 plus 3 or the sum of them. So kind of back like this, how I just messed this up. But if you have a 9-volt battery and a 3-volt battery, and you have the positive sides of the battery touching, the total voltage in the circuit would be 6, 9 minus 3. It messes up because for the last class, I had this in reverse. But basically, whenever you're going to get symbols like this, whenever you see that these two middle pieces are the same, you know that you subtract these numbers. If you have a question that has them like this, where you have negative, positive, and then you know you can add them together. So again, it's just showing the maximum or the best way to have voltage, and also how to calculate voltage. It's really not that challenging to calculate voltage. So we really never talked about it at the beginning. We always were just given whatever our voltage was because we didn't really deal with that. But so that's really all you need to know about batteries. So just kind of know, like, again, you don't have to know why a battery is a cathode, electrolyte, and an anode. Just know that they flow from negative to positive and they all get stored in the anode, which is where they start to flow. Know that the batteries and voltage have the same voltage. All batteries have the same voltage in a parallel series, and know that they do not have the same voltage in a series circuit. And in order to find the total voltage, you just take the difference, unless of course it's a situation with the two positive ends touching, then we subtract. Okay, so that is all I have. So I'm gonna stop my recording.